Okay, so this is a lecture about Verilog. We're gonna talk a little bit about the syntax, the code, and then for the second half, we'll be writing code together and see how it's done and how it's simulated and compiled, and what software you can use for it. So I'm gonna go through this quickly, and some things you might not understand. So you're always encouraged to look up tutorials on your own, and I'll send you this link to this presentation and other tutorials online. You can look it up. Okay, so say you want to design an adder. What is the hardest way to do it? The hardest way, if you want to be really bad with yourself, give yourself a hard time.
Layout.
Yeah. Okay, you'd use layout. Right. The second hardest way would be to just use a schematic and use transistors. The third hardest way is to just use gates maybe. And then you could use modules. You have a 1-bit adder and you use that module to create a multi-bit adder. Now after that you come to the easiest way of doing adder. And this is where you would meet Verilog or VHDL, which do the same thing really, Verilog and VHDL. VHDL is a little bit older, I think, but now Verilog has caught up with it, and I think it's more popular nowadays. So Verilog is called Verilog HDL because it's a hardware description language. You describe how the hardware will be. The HDL is also in HDL, same thing. You write the code, as you can see here. The code is then synthesized using software like Synopsys into a netlist. This netlist can go into an ASIC, which is a custom layout, or an FPGA, or a PAL. Okay, so the first thing you think of in Verilog are modules. Everything is a module. Whatever you want to create, you create it in a module. And then these modules you use inside other modules. Think of it as in C++. C++, you always have a function. Even if you have only the main function, you always have a function. So here you always have a module. You can create comments using these two lines here, just like C++. You can also create comments using the slash and star. Okay, so here they're creating a module of a multiplexer 2-to-1. You can see here, you write the module keyword, you always write that, and then the module name, and then the ports. And then you can specify here what type of ports you want. Now in Verilog after 2001, you can actually specify the type of inputs or outputs here in the parameter list, which is easier. And then here you would write your code, how you describe your hardware. And this is what it would look like multiplexer. Okay, now there are 3 ways to describe hardware in Verilog. There is okay, let me skip this part. There is the simplest way, which is the simplest being the hardest actually. This is the gate level description. This is almost like writing, like doing schematic yourself, except for connecting it using wires and stuff. You connecting using writing code. Almost like writing SPICE actually. So this is how you would design a multiplexer using gates, using AND gates and an OR gate at the end. And you could do that in Verilog writing, like first you would place an AND gate like that, and you name your AND gate as A1, and the first argument is the output, and then the 2 inputs, and so forth, even for your inverter, which is called NOT. These are constant modules, by the way, always there. You can use them in your designs. By the way, to connect them, you also need wires. That's why you create wires here. These are internal wires which will not be visible to the outside, which are not ports to the module. And finally, if you want to, okay, now here's this statement, assign. This is cheating here. This is not gate level. This is on another level, but they put it here. I don't know why. It's cheating. The second level, which is the second hardest, the second type of writing Verilog, is called so the first one is gate level, which is structural. The second one is procedural. I think that's what it's called. No, behavioral is the third level. You have 3 levels. The second level that I'm talking about is using assign statements, as in here. It's called data flow, actually. Yeah, that's what it's called. So instead of placing the gates, what I do is that I assign out to be equal to this statement here. Now this is a statement that you find in almost every programming language. It means if select is 1, select A. If select is 0, then out equals to B. And this here is the not operator. Put out bar equal to not out. Now this is easier than placing gates, right? And it accomplishes basically the same thing. So if you could do that instead of gates, you are encouraged to do it. Okay, this assign statement, whenever you assign, I have my output here out, I assign it to this. I cannot assign it back to another thing. This is fixed. I assign it, I connect it physically. I can't disconnect it at another time. Okay. So you could see this code is much shorter than this code. Although in this code you have a more physical picture of your design. Okay. Now let's talk about registers. We've only seen wires so far, but you can also create registers. Now, when you create a register in Verilog, it doesn't mean that when you synthesize it, it's going to be a register in actual hardware. It doesn't mean it's going to be a latch or anything that's controlled by a clock. Actually, it will only be this way if you specify your design as synchronous. If actually the compiler sees your design as synchronous. But use the reg keyword to create a register, as we'll see here.
Is this going to be synthesized?
It's not necessary that you would have a register. Okay. The reason you may want to have registers in your code is to simplify the description of your hardware. Think of it as variables in C++. You create a variable. Yeah. Registers are synthesizable in all cases. Registers, you can change their values later, like variables. You can assign them a value and later on change their value and use their values in another registers and stuff. So you can create complex relationships using registers. That's why you'd use them. This level is called behavioral level. This is the most abstract level, the top level of Verilog. And this is where you never know what the synthesizer is gonna make of your code. You never know the physical connection, what gate is gonna use, what register is gonna use. You only know how it's gonna behave. So that's why it's called behavioral. In behavioral, now behavioral code is always placed in blocks called begin end blocks. You begin and you end, and you put your behavioral code inside these keywords, begin and end.
Before finishing that, I'd like to ask about the difference between wire and register.
Wire and register.
These are definitions for input and output ports, and he also says that the wire means that doesn't hold the value.
A wire, you can assign it, but you can't change its value. You assign it once, you connect it physically to something, you cannot change it later on in your code. It's fixed. A register, you can do whatever you want with it later.
On that node, right? But
Yeah.
I can do the operations afterwards to the wire. It was an empty.
You can use the wire in other stuff, like
Yeah.
you can use it as an input to other stuff. Yeah.
But register, I can change it.
Yeah, you can
It will
change.
hold the value.
Right. Yeah. It's important to note here that inputs can be wires, but they can't be registers. You can't have inputs to your modules going straight to registers. That's not possible. So your inputs have to be wires and not registers. Your outputs can be either wires or registers. Okay, so we said behavioral will always be inside begin end, and the begin end has to be in an always block. I'll explain what always block is now. They're actually an always block and an initial block. Initial block is executed once, always block is executed continuously. Initial block, you'd only use that mostly in test bench. You'd rarely use that in actual design description. Okay, so this is how the always works. Always will take a sensitivity list, meaning it will do this block here, the begin end, whenever any of these signals change. If A changes or B or select, it will do this stuff. So what does this remind you of? Is it combinational or is it sequential? What would be the outcome of this? Why is it sequential? This is you see it in sequence here, but is it actually in sequence? This is actually combinational, because the output will change whenever the input changes.
Not like
The HDL. I'm not very familiar with H, but yeah. So this is combinational because it's triggered on any change in the signals. This is how combinational works. Anyway, you see here the description. If select, then out equal A, else out equal B. This is very familiar to how you would program actually in C++. And here we're actually mixing behavioral and continuous assignments. So you can actually mix the three styles of programming together. You could also use case statements, you can see here, and the always begin. Now, always have to remember, this is a common error. All of your behavioral code can only be in begin and blocks inside always blocks or initial blocks. A lot of times people put it outside the begin and or in always, and they wonder why they got compilation errors. So keep that in mind. Also, you cannot assign wires inside always. Okay. Now, everything we did so far was for a single bit wires, single bit. So what if we want an 8-bit multiplexer or an 8-bit wire? This is where we create vectors or buses. And to create a vector, we specify the size right after the type, if it's input or output. Oh, sorry here. So it could be either input, output, or register, and this is an 8-bit register out. And then you would work with it normally, as you would as you would if it was 1 bit. Although you could, if you want, specify part of the signal, like the first 3 bit, the last 3 bit, or specify individual bits.
But you can like write mixture of behavioral, gate level.
Yeah.
That's like in the same.
You can mix them all together, but you have to obey the rules. Behavioral only inside always blocks with begin end, or initial blocks with begin
Assign
end.
outside.
Assign outside, yes. Okay. Now, you could see here, we created a 32-bit adder using 3 lines of code to tell you how easy it is to program Verilog. But the problem here that this does not provide us with carry in and carry out, the first example here, right? So how would we implement that, carry in and carry out? You see this statement here, assign cout sum. This syntax means concatenation. Concatenation meaning it like stitches them together. Think of them like right next to each other. So this is sum followed immediately by cout equals to a plus b plus cn. So if we had an overflow in the sum, it will pass to the cout bit. Concatenation is very common in Verilog. This is one of the mistakes you can do in Verilog. Okay, so we said that this here is combinational, correct? How would we actually do a sequential design? We have to have a clock, and the always block would be triggered not by a signal change but by a certain edge. You guys remember flip-flops we talked about? Only change on the edge, like negative or positive. So here we say always at positive edge of the clock or negative edge. And this is how we can do synchronous clear and asynchronous clear. Synchronous clear will clear the value only at the clock edge, and asynchronous clear will clear the value in the flip-flop whenever the clear signal goes up, regardless of the time inside the clock cycle. So you could see the implementation here. Okay. Now sometimes, actually a lot of times, you will see this syntax being used. Instead of just writing equal, we write less than and equal. This is not a comparison. This is an assignment, just like the equal. The difference is that, okay, let's consider the first case. In the first case, we do x equal a or b, right? We finish this statement, we have a value for x, we move to the second statement, y equal a or b or c, and then c, and then z. So the point is, we wait till x finishes, so we move back to y. If we want to use the value of x and y, it will be the new value after it was computed. By contrast, if we execute it here using the non-blocking assignment, these will not happen together. I mean, they will not happen sequentially. They will happen at the same time. So if you were to use x in the statement here of y, it will be its old value before it was computed again. You guys understand this point? Okay. Over here, actually I need a better example to... Okay, this is a better example. Q1 equal in, right? And then we do Q2 equal Q1. Does this mean Q2 equals in? It should, right? But it doesn't, because this type of equal is not an equal that happens sequentially. It actually postpones all the equal and does them at the same time at the clock edge. It won't do them together. It won't do them sequentially.
However, the begin and include sequential. Both of the statements inside the begin include.
Yeah, it will do
They
them.
are
It will do them. It will do them sequentially.
But this sign means that even if it is in the begin and include, they are by executed pattern.
Right. Yeah.
So the statements within the begin and end are sequential.
They are sequential by nature, unless you're using this symbol here.
And the parallel execution here, for example, will be end as if we exit from this block. Like after end, it will be the new value.
Yes. Yeah. You mean in the one here?
Like if I wanna use Q1 for the new value, it will be only after the begin end block.
Yes. After all of them have finished. While in here, Q2 will actually be equal to in, and out will actually be equal to Q2 will be equal to in. Okay? Now, this is actually how real hardware would work. Closer. This is closer to how real hardware would work. Because at the clock edge, Q1 has not finished computing yet. So when we assign Q2 to Q1, it will be its old value. This is actually much more similar to how hardware works. And it will be synthesized like that. Okay? That's how it will be synthesized. The first one, the non-blocking. The blocking would be synthesized just like this. It's a wire. Because we're saying Q1 equals Q2. So it will just connect Q2 to Q1 using a wire. And out to Q1 using a wire.
If Q1 is finished, the value.
Yes. Yeah. So be careful which one you choose according to how you want your circuit to behave. So this is for using blocking for combinational logic. Yes, combinational logic use blocking, which is the regular equal sign. Whenever you want to produce blocking combinational. As for non-blocking, you would use it in sequential circuits, since as is usually thought of in sequential circuits, everything updates on the clock edge. Okay.
But most of the computation units is combinational, right?
Most of the
Just which do computations. It's not sequential.
most of the you're saying most of designs are combinational?
I mean that which do computation, like most of the
Yeah.
computational units. And I think the memory units are more sequential.
For instance, dividers are sequential because you can have combinational dividers, but by doing sequential dividers, you reduce the size significantly. Instead of taking a single clock cycle and taking a huge area, it takes half the area and does it in 2 clock cycles. Especially floating point units, they're really big, so you do them sequentially. A lot of elements are actually sequential. The controller, state machine, you have to do them sequentially. Okay. Now, have you guys heard? Of course, you've heard of encoders, right? If I want to supply this, these are the inputs, these are the outputs. If I supply 0, 1, 0, 0, I would obtain 1. If I supply 0, 1, 0, 0, I would obtain a 2. So this is an encoder design. And this is how, this is one way we could implement it. But is it actually correct? And why would you think, what would you think is wrong with it? There's something wrong here. So what do we mean by I0 here? No, I bracket first, yeah, first bit of I, and this is second bit. And here always at I means whenever any bit of I changes. I is 4 bits. Hmm? Output's 2 bits, yeah, so.
Let's suppose I is 0, 1, 0, 0. If I of 0 is 0, and that satisfies, so 0, 0 is assigned to output.
No, this computes if I of 0 is 1 only.
Okay.
Yeah.
We haven't defined the input I either is wired or
When you don't define, it defaults it to wire.
wired.
Yeah. So the error here is, suppose we give an input of, let's say, 1, 1, 0, 0. What should be the output if it's 1, 1, 0, 0? To actually explain it really well here.
What's meant by if?
Oh, yeah.
What's meant by if I of 0? What does it mean if it's 1?
I mean, if it's 1,
True.
yeah. It's the same as if you say equal equal 1.
Here you check by bit by bit. But you have to check the whole.
Right, yeah. So if we get 1, 1, 0, 0, it will assume that it's 1. I mean, it will assume that it's 0, actually. While it should be actually XX because it's undefined. This can only accept 4 types of inputs. 0, 0, 1, 0, 0, 1, 0, and 0, 1, 0, 0, 1, 0, 0, and all others should be XX. Well, in this case, whenever it encounters the first bit, it outputs the result. It should check all other bits at the same time. So this is how you would solve it. You actually say if I equals 4, comma, not comma, I mean apostrophe, B 0, 0, 0, 1, E equals. So if you don't know this syntax here, 4 designates the number of bits you're considering, and here B, it's binary. You could actually use D for decimal and H for hexadecimal, and I think O for octet. I'm not sure. What is it? X? No, 0x is in C++, I think, for hexadecimal. Okay. And, okay. Now assume you've created several modules, you want to connect them together. And this is how you should always do your code. Find the smallest module, implement that, and do it hierarchically. you have multiple files, multiple Verileg files with multiple modules. Okay. So these are the module definitions, and this is how we would place the modules inside the code. First, you would write the module name that you have it that's already defined for the module. For instance, here we created a module called add32. So if we want to instantiate one instance of that module, we create as many instances that we want. We write add32 here, whatever name you want to call the adder. It doesn't matter. And then you put the name of the ports that you have.
But those modules are defined within the code itself? Should be defined, right?
No.
Because I tried to use modules outside the code and doesn't work. I should put the module itself inside the code.
What do you mean inside the code?
I mean when I am writing a code to build like a module for my code, and then after that I'd like to use add32. Okay, I should like include this module inside the whole outside my module.
Are you saying that inside the other module? No, you should never do that.
Outside the module
Yeah.
I am building, but in order to call this module, I have to include it within my code itself.
Yes, yeah. It should be inside. If it's not inside the same file, if the two modules are not inside the same file, they're in separate files, you'd have to supply the two files to the compiler, and the compiler would figure out that they are in two different files. Just like C++, actually. We'll do an example right here, actually. The ordering of the parameters is the same. I mean, the inputs and outputs is the same as the ordering that you define when creating the module. Also, here, for the adder, my output is sum. It's the last port that I have. If I want to place a register here, I can't. I cannot place a register on the output from the outside of a module. Inside the module, it can be an output, the register. Outside of a module, I cannot connect to a register. It has to be a wire. I can connect the register to the input of a module though. Okay? You have to look at the big picture. Here actually you can switch the ordering of the ports if you want using this this syntax, but you would not normally need to do that. These are the Boolean operators that you have. Here you should these are familiar to you from other programming languages. These here might be new. This is not AND or XNOR. Okay. Now, a very important concept in Verilog are test benches. Test benches is, suppose you create an adder module. If you want to simulate it, you should never put the simulation code with the same file or the same module. You create another file called a test bench in which you instantiate the module, you give it inputs, and you monitor the outputs there. Again, I'm going to do a demo right here.
Because I cannot define the input ports and the output ports when I put them in the definition itself.
It's not that you can't. You can easily simulate the module from inside itself, but it's not organized to do it. It's not recommended.
I think I simulated that using the inputs and the outputs defined in the module definition, and synthesize modules.
Yeah.
You shouldn't like give values.
Yeah, if it's a module you want to synthesize, you should never give values inside of it, like test values. It should be a module by itself. Okay. And this is advanced Verilog. This is actually not very advanced. Parameters are very popular. Parameters are, suppose I want my adder to have a variable width, not a fixed width. So I define a parameter, say width, and then instead of writing 4, I just write width minus 1. And if I want to change my design, if it want to change the width, I just change the value here, everything changes. In fact, when I instantiate this module, I can specify the parameter from the instantiation statement using this syntax here, which you'll also find useful later on. These are not very useful, very long. Okay, so let's create an example. What should we create? An adder, a logical function. Okay, let's create an adder. We'll create it in actually 3 ways for you to get familiar with it. Let's call it adder1.v. So first we start with module. Here I can say whatever I want, so I'll just say adder1. I'll have an inputs A, B, and C in. My outputs would be out and C out, and then I end with a semicolon. And then I add my module, just in case I forgot later. And here I specify my inputs. First, let me specify a parameter width equals to 8. My inputs are 8 bits, right? So it's width minus 1 till 0. A, B, that's it. And then input Cin. And then I specify my output. Cn would be 1 bit. If I don't specify anything, it will be 1 bit.
1 bit.
Yeah. And output will be also 1 bit, like that. Actually, I cannot do it in gate level because it would take forever here. So I'll just do it first using data flow. Is it data flow? It's not data flow. I'll just call it procedural or continuous assignment. So assign C out. By the way, Verilog is case sensitive, so if you capitalize something, you have to capitalize it everywhere. C out equals to what? A plus B plus Cn. Right? That's it. I just created my adder. Now I want to simulate this adder, right? I never write the simulation code here. I create a new file. Sorry. Create document. Test adder1.v. Module test adder1. By the way, test modules do not have to have any inputs or outputs. It can, but it's usually not needed. So, okay, if I'm gonna test my adder, the inputs to my adder, I want to change them constantly, right? So they better be what? Registers. parameter equal to 8. So register width minus 1 0. Oh. AB, and then register CN. It doesn't matter if it's the same name, they're on different levels so they don't conflict with each other. And my outputs would be wires because I'm only monitoring them, I'm never changing them. So wire width minus 1 0 C out, and then wire, I'm sorry, this is out and this is C out. Okay. Now I don't do an always block here because I'm only simulating once, so I do an initial block and then begin end, and I put my simulation code in here. First, this is specific to the software that I have. You don't have to do it if you're using Model Sim or Xilinx, but because I'm using a special software here, I start my code using, I have to put these two statements. Okay. Dump file. This is a waveform file I'm going to generate. I'm going to call it add out.vcd, and then I'm going to store the variables dump vars. Zero, and here I put my module name, test adder 1. Okay, now I put a equals to, actually I haven't instantiated my module, so what I do is adder 1, my adder, and A, B, C in, out, C out. So I've connected my elements here.
What you did now is instantiation?
Yes. If I don't specify the type of the value 56, it's always decimal. That's the default value. Even if I write 1 0, that's 10, that's not 2. And then B equals to 13. C and yeah, everything is decimal. Okay. And then this is very useful to put a delay. Actually, in test benches, you need to put this on top. This means my time unit is 1 nanosecond. My precision, simulation precision, is 10 picosecond. So here I want to put a delay of 5 nanoseconds, and then change the value of B to 100, and then after 5 nanoseconds I want to change the value of Cn to 1, and here I finish. Also, the finish here is not required if you're using Model Sim or Xilinx. Neither are these. Okay, time for simulation. Desktop, Verilog examples. This command I use. Now this iVerilog, it's called Icarus Verilog. It's a Verilog simulator. It's open source and freely available for both Windows and Linux, so you can use it on Windows or Linux. Test adder 1, adder 1. I have to supply both files because if I only supply test adder, it's not going to know where my adder is. And my output /o is, let me call it my outs. Okay, no errors. Great. This is just compilation stage. The simulation is VVP. This is also part of the same software, Icarus Verilog. And I simulate my out. It tells me that it generated the waveform. So here I'm using a second software called GTK Wave. This is also freely available software, open source, for both Windows and Linux. So you could use this. You could do your work on Windows if you want. And oh, I have 3Ds. Okay. So these are the signals that I have. You can select them all, put them here, zoom to fit. Actually, oh. Okay. It's supposed to work. Anyway. Here it's displaying it in hexadecimal. I want it to be in decimal. Okay, the software should be more friendly than that.
So when, on what stage were you using it after we started coding the Verilog
Yeah.
and generate them?
You can do them simultaneously. You can, one member of the group can work in Cadence, another can work in
I mean,
the
when do
Verilog.
we incorporate the code into or we don't?
You never incorporate the code into Cadence. You just do the layout there simultaneously.
Also, there is no link between the code
There's no what?
and link between the code and
No. No.
Cadence will have sense.
Actually, you're gonna use a new part of Cadence called encounter to generate the layout from Verilog, but that won't be related to you actually drawing the layout, which you should do for a very small module of your code, like about 40 gates, nothing more than 40 gates.
The values of the C out
Yeah.
won't work.
Yeah, because Cout did never changed. It never exceeded the 256. Cout will only become 1 if I exceed 256, right? When it overflows. I don't have any carry here. But Cn is supposed to change. How come it did not? Oh, I'm sorry. There should be a small delay there for me to see. Oh, I have to simulate again. It's not nice. I wonder if I can update the result. Doesn't look like it. Oh yeah, I can reload. Yeah, you can see Cn changed here, and my final value changed to 157. Yeah, the zoom is messed up. The problem was that I didn't place enough delay after changing Cn. for the simulation to appear. It was ending, the waveform was ending before, so.
The end of the simulation was before. the
Right.
change.
Right. Okay, so you guys have many choices when you want to write Verilog simulated. You can download these two software, Icarus Verilog and GTK Wave. Install them either on Windows or on Linux. Or you can download ModelSim. ModelSim, they only give you a free license for 6 months. When it expires, you have to download it again. And I think it's only available for Windows. Xilinx, you can get Xilinx Webpack version, which is the free version, but it's big. It's like 4 gigabytes. You have to download it, and
Based on experience, which is better? Also,
actually I prefer this one because it's very fast, very lightweight, and never expires. It's free. You might have a little bit of hard time to set it up, to install it.
this.
Yeah, because there are two separate software, one for viewing the waveform, one for actually doing the simulation. Especially in Windows, because when you install a software in Windows, it doesn't add the command to your list of commands. You have to go into the system settings and add the path to your software so that it's inside. Yeah. But yeah, that's my personal choice. But many people find ModelSim more user-friendly, graphically more user-friendly. But it's very buggy. I really don't like how much buggy it is. And Xilinx is a huge and slow. It takes forever to do the simulation. So this is my personal preference. Anyway. Okay.
Can you send us like the URLs?
Yeah, sure. I'll send you the instructions. Any questions? Okay. I have a very lightweight class today. Slimmed down class.
You have